So I think we are all here now. We are missing a few, maybe. One of the speakers is missing, so I'm a bit concerned of that. But hopefully he's in the afternoon, so that will probably solve itself, I hope. So a very warm welcome to this seminar that we have today. Firstly, there is no planned fire exercises or anything like this. So if the alarm goes off, we go out through these two doors there. Not there, but there. And then the rendezvous place is on the parking space outside, so you know that. My name is Andreas Back, and I'm the director of Lighthouse. And for you who doesn't know who we are, Lighthouse, we are the Swedish collaboration platform for maritime research and innovation. And what we do is that we try to support the maritime business and especially the shipping as best as we can. And we do that by, for example, this type of seminars on topics that the industry thinks are interesting. We run some focus groups. We have 3 focus groups. One is fossil-free shipping, the other one is sustainable ports, and the third one is smart ships. And they are free to attend, so if you are interested in any of those subjects, please contact me, or Lasse, who is filming today, who is back there, or Caroline, who is, she's not here right now, but that was the woman welcoming you all here. We do also have a trainee program where we try to get young people into the maritime business. We do some communication and knowledge sharing, mostly Lasse that does that. We have a national research program called Sustainable Shipping, eller Hållbar sjöfart, where we fund projects within the maritime industry. So if you have any great ideas of interesting developing projects, please contact us as well. And then we do seminars and workshops. That's really short about Lighthouse. I think this would be a really interesting day where we can learn about CCS, both on board and on land. The program today is we have 10 presentations, and in between there we will have some coffee and some lunch and so on. The coffee breaks and the lunch break are quite long, and that's because we really want you to talk to each other. That normally that is not a problem with this crowd, but take the chance to network and discuss with colleagues and so on. And if you get any great ideas, contact us. So I think that's it, and we will just get started with the day. And first out is Kalle. And he will start with a short overview of CCS in the maritime domain. So please welcome up Kalle. He's already here, perfect. And Kalle is a project leader and a researcher at the Swedish Environmental Research Institute, IVL. And Kalle is specializing in the transition of shipping towards sustainable fuels. And also Kalle is running one of the focus group, fossil-free shipping. So,
which you all are very welcome to participate in.
Yeah. So please go ahead, Kalle.
Thank you. What an honor to start this fantastic day. So I'm a naval architect, and I've been working with the shipping transition towards more sustainable operations, fuels, and so on. But myself, as well as IVL, has also worked a bit with carbon capturing. Myself with carbon capturing on board ships, and we did, for example, a Lighthouse report that was released 3 years ago, almost. And it was about the potential of onboard carbon capturing. And Selma, I don't know if she's here, no, but Yeah, you were a part of this as well, where we assessed the technology at that time. We looked at ways to assess in a systematic approach which technology that would fit for a specific ship and so on. And we also looked at where the technology and the applications were at that time. And I still think many of the results is valid, and there is like a full description of the technologies and so on within that report. That could be worth looking at for anyone that is looking at that. We have also worked with Hannes at DNV for where the whole industry is heading and what kind of challenges that the industry has. Not only the shipping industry, but also like the power plants that would like to capture their carbon and deliver it somewhere, either for usage for in the chemical industry, making new fuels, or for permanent storage in the ground. And we are now working with the DNV in another lighthouse project where we are looking at if and how the amount of carbon captured on board ships, where it should be delivered, how it could be taken care of within the port as a hub or something like that. And so DNV is looking at the amounts and making potential studies for how large amount of CO2 that could be delivered into the specific port, and we would look at the economics and the technology for delivering it ashore. We are also a part of another project, CCS, an EU project that I think Xuan from RISE will talk about later today, where the whole infrastructure, the marine infrastructure for transporting captured CO2 from port as a hub or somewhere else towards utilization or permanent storage. So design of the ships and the logistical setups and so on. So we are active in the field, but I must admit I'm not an expert on carbon capturing itself, but I'm going to talk about it because Andreas asked me. If we're talking about the carbon that is captured on board ships, it would also make sense to look at the potential captured volumes for the land-based systems. It would be very, very costly to build up systems just for the carbon that is collected on board ships. So you would probably want to find synergies with the systems that is developed for the land-based sources. So that is interesting, and there is also already studies today about what kind of systems that could be built up, making hubs within ports, and we know that many ports are interested in looking at this and so on. So that's an important part of it. Related to the technology, there are many different ways of collecting the carbon or the carbon dioxide from the exhaust or from the combustion process. We could of course collect it before the fuel enters into the engine, pre-combustion capture. We could have an oxy-fuel combustion where you burn the fuel together with oxygen, and out of the engine as exhaust, then you would get almost just carbon dioxide, which then could be used. But the most common way is post-combustion capture, and that the benefits with that is that you normally don't have to alter or change anything within the combustion process. So you could use the same engines and just add something afterwards. But this could also be made in different ways. You could have a chemical absorption, you could use a membrane, you could use heat exchange in a cryogenic system, or a calcium looping. So, the most common or most worked with system is the chemical absorption. And then you often use some kind of chemical solvent like MEA, monoethanol amine. There are many others as well. We're going to look at that as well. So you could say that you scrub the exhaust, the solution captures the carbon, and then you release it in another step. And the MEA solution is often used as a benchmark when you're comparing systems and so on. It's the most common and still used system. But there are many, many other solutions as well. So with different pros and cons. I'm not going to go into that, but some are more poisonous, some are more costly, some have better energy efficiency, and so on. Absorption by solid sorbent and membrane technologies. You could, for example, use a calcium looping process. So you have calcium oxide that reacts with the carbon dioxide, and then you get a calcium carbonate that could be delivered ashore and used for other processes later. Within the cryogenic carbon capture, you take the exhaust gases below 100 degrees Celsius minus, and then you could loop out the carbon dioxide. And it's actually this system that we found the most promising. You have the possibility to have less energy used for the process. It might be the most economically feasible in the future, and so on. And it could also take up less space than other systems. Then you have the pre-combustion, where Chalmers, for example, and Selma and other colleagues have looked a lot about within their HIMETH project, where you take out the carbon before the engine and then run the engines or fuel cells just on hydrogen. And then you have oxy-fuel combustion, where you instead of using air for the inlet to the engine, you use pure oxygen or a mix with oxygen and air. If you use pure oxygen and fuel in the combustion process, you will get almost just carbon dioxide out of the engine as exhaust, and then you could take care of that easier. And if the development of fuel productions will become more towards e-fuels, such as hydrogen or e-methanol and so on, you will get a lot of oxygen from the production of hydrogen. And that might be interesting to use within oxy-fuel combustion. So that could be like a possibility as well in the future. Why are we talking about onboard carbon capture? And I think the main reason is that it's most probably that fossil fuels will be used on board ships for a very long time. And in order to meet future targets of decarbonizing the shipping industry, carbon capture is often seen as a prerequisite for meeting those targets within the models and so on. But so far, it's been very much of pilot and test installations, but now we see some real installations. And I think maybe Lang and Versili will talk more about that later today. The main challenge, as we see it, still, it's to build up the logistical system for taking care of the carbon captured on board and delivering it ashore or via like a bunker vessel for carbon dioxide, delivering it either to another ship, taking it to a storage point or something like that, or ashore. This is maybe not so technically difficult, but we don't have the systems today, and we don't have really decided how the most efficient systems looks like. So if you are installing a system on board today, it's kind of costly today to deliver the carbon dioxide ashore. As I said, we made up a scheme for assessing the different technologies on board ships, and that's still a valid method that could be interesting to use. We did some assessments 2-3 years ago, and we found the cryogenic carbon capture the most promising, but of course the chemical absorption and others are also way to go forward. We can see, we talked, for example, to Solvang, a Norwegian shipping company, a week ago or so. They have installed a full carbon capturing system from Wärtsilä on board their ships, and they are capturing about 90% of the carbon dioxide from their engines. They also claim that the delivering ashore is their main problem that they need to find a good solution for. So, all in all, it's not a... I think someone is calling here. And I'm not... Okay. So, it's not a technical problem to do this. To find a good business case and find the systems for delivering ashore is probably the most challenging things. And as we see, the cost for onboard carbon capturing has been lowered over the years. And but to make this fly, we probably need an efficient system for the logistical setup for taking the carbon captured from the ship towards the end use or storage. So I think that was what I had to say. And yeah?
I have a question here.
Yeah.
You have to...
Wait a second. We need...
Since we are streaming it, people have to hear lines, so that is why you have to have a
Thank you.
mix. Yes.
I can speak louder. Yeah. Can you in some way say, for example, if we have Stina på ferry to Kiel, back and forth here. It's around 24 hours and around 800 kilometers. How much carbon is it you should take care about around?
Yeah, so you could say that roughly it's if you burn 1 ton of fuel,
yeah,
like MGU or something like that,
yeah,
you will get 3.2 tons of CO2.
Yeah.
So if we look at the system on board, for example, the Solvang vessel, you could see the tanks on the deck. It's kind of large systems. Those containers or tanks for carbon dioxide here is like, I think they would fit some 700 tons of fuel. But that is probably for a trip, at least from Europe to US or something like that. So, but it's a very relevant question. How much carbon is it that you will allow to capture on board? And I don't think that ferries running between Sweden and the continent would be a problem. But if you're capturing carbon and go for a trip all over the world, then you would need kind of large storage tanks.
Right.
Yep.
Thank you, Kalle.
Yeah.
Any more questions? Here we have one.
Thank you, Kalle. I have two questions. First, I wonder if you could say something about the energy demands for running, especially the chemical absorbent system, because I've seen quite estimates that say up to 40% of total energy needs to reduce CO2 emissions by 80%, which is extremely an extreme penalty, of course. And I also wonder if you have seen any studies that models future costs for getting rid of the CO2.
So the first question, it depends a lot on how you could integrate the energy balances between the capturing system and the engines. How much excess heat do you have available from the engines and so on? And as I understand, there is like a trend with some going for less captured rate, so that you maybe just capture 10 to 30% of the carbon from the fuel or the exhaust, and that's because then you could run the system more just on the available heat. There are plenty of calculations available, but I don't dare to guess for the moment. And the other question was about the cost. So we are actually trying to find figures for that. I don't have any for the moment. I know, for example, when we talk to Solvang, that they are paying a tremendous amount of money today to get rid of the carbon, but they hope, of course, to get it a lot lower. Maybe Wärtsilä and Lang can elaborate on that later today.
All right. Then one more question. All right. A quick one. Johan.
Hey, Kalle, do you know what pressure and temperature that Yara vessel is storing the CO2 on board at?
No.
Okay.
No.
That was a perfect short question and a very short answer. I like that. Thank you. So, thank you, Kalle. So, from IVL to DNV. Please welcome Hannes von Knorring to give the DNV view of Energy Transit Outlook CCS to 2035, right? Or 50 even.
Yes, very long time.
All right. So Hannes is a principal consultant at DNV Maritime. He has been working with decarbonization in the maritime sector since 2009, from energy efficiency to alternative fuels to CO2 shipping and AI on board. So a lot of stuff there. Hannes is also a frequent participant in lighthouse projects.
Yes.
Yes. So please go ahead, Hannes.
Thanks. Yeah, 2009, that was a great year for maritime. It was when a new generation of PhD students started here at Chalmers, and a couple of them are here on environmental issues. Yeah, Fredrik and where is Selma, and yeah, there you are. And so I've been in shipping since then. I'm not a naval architect, but I was just drawn in by the industry and all the interesting things that are going on. I've been in DNV for 5 years now, and I work as presented across a range of topics. CCS is one of those topics I think where I'm very much not an expert. So, but I do have a lot of expert colleagues that have put together a lot of material. And if I'm not able to answer, I will find one of them and ask them. So on DV side, we have the maritime side, which I represent, but we also have the energy system side, which is actually larger than the maritime part of DNV nowadays. And it is here that we do a lot of activity related to carbon capture. The current count is 400 plus projects. We are also putting a lot of work into developing international standards and our own recommended practices in different aspects of safety and performance related to CCS. And we work across this whole value chain. We have also interesting a series of labs and technology centers where we can test things and break things and have CO2 pipelines explode and all those exciting things, see what happens. On shipping, we are of course involved in class and advisory with current vessels in operation and also the new vessels that are being operated out of the Northern Lights. We're also working across the value chain on other pressure regimes. So if the current pressure regime is medium pressure, we're also working a lot on elevated and low pressure chains. And here are some examples of standards and practices that we are developing together with others on CO2 specifications and also an ISO standard. But I was not asked to talk so much about the technical aspects of CCS, but rather, so how does it fit into global decarbonization and maritime decarbonization. And here we have kind of a different set of expertise, and that is energy systems modeling. So we have a fairly large research group dedicated to developing and using models of the global energy systems to see how it will develop. And specifically, this model is about making scenarios into the future based on current trajectories. And the latest forecast is that we are heading towards what can only be described as a catastrophe for many parts of the world, a global warming above 2 degrees. Even though we are now reducing emissions, expected to be reducing emissions rapidly, and even having negative emissions from mid-century, we are still overshooting this 2-degree budget by quite a large amount. So emissions, as we see in this modeling, doesn't even halve by 2050. A lot of things are expected to happen. We see a massive expansion of electricity coming from renewable resources, mostly wind and solar. We're seeing a shift away from oil in the transport sector. So we have rail, maritime, road and aviation not dropping to zero 2050, but still rapidly. In road, this will be mostly because of a large uptake of EVs. And in maritime aviation, we will see different fuels and also carbon capture. And interestingly, this since the transport sector is such a big part of driving demand for liquid fossil fuels, the fact that we will be reducing emissions and demand of fossil fuels so much in the transport sector means that we will see much less shipping of fossil fuels, meaning that we will actually be seeing a decoupling of shipping trade from GDP growth. So here we can see the different, we can see fossil fuel declining towards 2060, and we can also see seaborne trade leveling out. So just a quick overview of the kind of the outputs of this model. What it also shows is a significant uptake of CCS technology. And this is just looking at the short term. This is not based off of modeling, but rather the projects that are in the pipeline. So whereas in 2024 we have around 62 million tons, we expect it to grow by a couple of 100% towards 2030, and then massively expand further to 1.3 million tons CO2 annually by 2050. After 2030, this will be mostly in hard-to-abate sectors, like different manufacturing sectors, but also in maritime. I haven't included any slides that needed for a net zero future, or that is perhaps even reaching 1.5 degrees. We have done those scenarios as well. That requires, I don't have the number, but a very much larger investment in CCS than this. And we expect it to take place a lot in different kinds of manufacturing sectors and other hard-to-abate sectors. So this is maritime transport. The dark blue is 2050 and the light is 2040. So in this case, expecting more in shipping towards 2050 rather than earlier. We have other scenarios that when maritime is forced to reach zero emissions by 2050, it becomes much larger. But in this global scenario, it is only appearing really at the end of the mid-century. So to the far right, we have different forms of ammonia and hydrogen production based off of natural gas. Of course, used a lot in fertilizer and in other parts of industry. We have a lot of biomass-fired plants being fitted with carbon capture, as is coal-fired and gas-fired, and then manufacturing, as we're seeing a lot in Sweden and elsewhere, on cement and also chemicals and steel. So these hard-to-abate sectors represent the larger share of these sectors which will be using CCS. So in this case, it is more than 75%. So I'm switching a little bit between scenarios. This is another piece of modeling work that we have done that is based off of the development of the global fleet in great detail. So here we have a representation of the global fleet in our time, and then simulating as that reaches zero emissions by 2050, and then using slightly different assumptions on the costs, relative costs of various solutions. So here we have 4 different scenarios that in different ways favor different outcomes. So we have number 1 here that favors use of biofuels. It has lower cost for biofuels. In the second, there are other assumptions that favor methanol, ammonia, and hydrogen. Reasonable but quite small changes in assumptions lead to very different results in terms of what fuels become dominant. But what I'd like to highlight is in all scenarios, actually carbon capture becomes a significant part from roughly 2030 and beyond. And if you look at it in detail, all of these different colors, you will see that after 2040, even vessels that are running on biofuels or e-fuels will also be fitting CCS carbon capture technology to reach zero emissions as a total. So it looks like CCS on ships will be an important part of the future for shipping. As we heard already from Kalle, it will depend a lot on the actual outcomes and the relative efficiency of various technologies. Here is one such attempt from our side to have high and low assumptions on CCS related costs for shipping related to other solutions, and we can just acknowledge that it is somewhere in this broad band of costs for other solutions. So we are still a little bit. It's a little bit too early to say whether this is for which segments and so on this is the best solution, but it is definitely well within reasonable bounds to being a popular solution to emissions abatement for ships. And one major reason, so you can just look at the order book and see that there are not that many vessels capable of using anything else than diesel. And this part of the fleet will need some sort of solution beyond, depending on how much biofuel you see as being available and at sufficient cost. Maybe CCS will be a solution for those vessels. But as we'll be discussing today, it is this connection between ships and the infrastructure that is already being built for land-based capture facilities that shipping can piggyback off on that development in the first stages. That will be crucial. Other than that, it is being well explored now. What do we have to consider when? So there are some questions about what the Stena ferry, for example, and there are these assessments being done for most kinds of vessels on what do you actually need to consider in detail. I don't have time, realize now, to go through this in all detail, but you can look at, there's a lot of research now that goes through different kinds of vessels and what are they different considerations that you need to take. And like Kalle mentioned already, available space, available heat, is it possible to integrate into existing, maybe there's even steam being produced on board that can be leveraged. And I want to jump a bit to the final estimation. This is one of those case studies where we look at what role can CCS play from a bottom-up perspective. Here we look at the largest kinds of vessels that they are, and that there are large bulkers, tankers and container ships. We make assumptions on reasonable tank volumes for different ship types. And then look at considering how these vessels operate, that we can follow these vessels and estimate what kind of voyages they do and how much energy are they consuming and how much CO2 can they store. And actually what we see in these simulations, that actually a very large part of particularly bulkers and tankers can actually carry their entire captured CO2 volumes. To a lesser extent, container ships, because of the way they operate. And if you add these all together and you look at the top ports, and if you build up this infrastructure, here you can see the number of ports, the largest port in order of size, and if you just pick the 20 largest, we could actually capture 19% of the fleet emissions. So depending on regulations, which we'll hear more about, I at least took those slides out, we can see CCS probably play a large role for ships. So we've seen a quick overview, the role of CCS in global decarbonization. We didn't talk so much about it, but the shipping is really what enables the CO2 infrastructure to be built up, and it will create entirely new vessel markets. Hundreds of vessels is being estimated in short and mid-term. The early adoption on board will depend on the shore infrastructure, and with the right kind of regulation and supporting standards, we could see significant emissions cuts from CCS in shipping. That's all.
Right, great. Thank you so much, Hannes. Do you have any question for Hannes?
You mentioned regulations, and many thanks for a good presentation. I at least see now at the moment a big issue being that it's not possible to report carbon capture in the MRV reporting. How is this? Do you know where is this going at the moment, and will it be soon implemented in MRV reporting?
Yeah, I had a slide on that which I took out because I didn't have time, and I saw that Hulda was going to say something about regulation, so I'll pass it on to Hulda.
And we had one question over here, right?
Thank you, Hannes, and thanks for a nice presentation. My name is Fredrik from the Swedish Agency for Marine and Water Management. So I had questions regarding your assumptions of the transition, etc. Do you also think that the usage of CCS on board can slow down the transition from fossil fuels? So do you take that into account in your assumptions? Or can you? Or do you want to?
This specific piece of modeling was just cost optimization and built off of what the current fleet looks like and the considerations taken every year. Okay, so what's the best solution for this vessel with this regulatory environment going forward? That discussion is big on land, right? That we are in, and you could see here on this. There were some slides here showing certain industries like and coal power plants being fitted with CCS to prolong their life, for example.
Yeah. Okay. Thank you.
Right.
So I mean, yes, it can happen.
Tricky question. One last question we had over here.
Thank you for a good presentation. Do you have an opinion on, let's assume that they ideally can capture most of the carbon on board in a nice shape and form, and then it comes to shore. Is it locally dependent, or do you have a firm opinion about what is the least costly way of disposing it somewhere? Is it cement, or is it underground, or do you have an opinion about that? Which is the most financially viable?
No, is the quick answer. This will depend a lot on what the regulation will allow, I guess, especially for maritime.
I'm talking money. I'm talking finance.
Yeah.
Because long run, that's going to decide.
Yeah, absolutely.
Regulations have an end of life, and then money will decide. So it's just if you have a model.
I will find the cost comparison and get back to you if you give me your card. Yeah.
Thank you.
All right. Thank you so much, Hannes.
Thanks.
So that actually concludes part one, the introduction part of today. And now we will hear from Hulda Vinnes about the challenges, which there are, I assume, quite a lot, of shaping international and international regulatory framework. So, Hulda, you has a PhD in shipping in maritime technology and holds a position as an advisor on climate and environmental regulations for international shipping at the Swedish Transport Agency. Yeah. Sprakar väldigt mycket.
Ja. Så kanske?
Ja.
Ja.
Lustigt.
Tack.
Varsågod, Hulda.
Thank you. Thank you, Andreas, and I'm happy to be here. Let's see if I can move forward to my presentation here. No? Hannes, what did you do? This is me. I will try and give an overview of the challenges with international regulations on OCCS. So my presentation will be on OCCS and not on CCS in general. So the regulatory certainty is, of course, very important in order to give the industry a chance to a willingness to invest in these new technologies. We are well aware of that. And we are not really there yet, as I'm sure most of you know. The EU has come further than the IMO. And so for the IMO, I will try to give an update on how the discussions are ongoing at the moment. But first I thought I'd just give a list of the different regulations which have or will need to have some provisions for the use of CCS. So we have EU and IMO regulations. And I will just go through them one by one as I see it. And we had a question on EU ETS before, but I'm just saying that this regulation is not within the Swedish Transport Agency portfolio, but in the Swedish EPA. So I have had some information from my colleagues at the EPA, but I don't have the detailed knowledge. What I've learned is that there are preliminary guidance available, and that CCS on board ships are treated similar to carbon capture in other sectors that are in the ETS. So basically it allows for accounting for reductions of CO2 if the CO2 is stored permanently or is used in a product, which means that it's chemically bound in a product that during normal usage will not emit any CO2. But I'm afraid I will not be able to answer your question on why it can't be reported to the MRV. I know the guidance is being updated, and maybe also the MRV formulas are being updated for that. But we can take your question to the right agency to have an answer. As for the fuel EU maritime, accounting of reductions of CO2 is not allowed, and that is because the fuel EU maritime is supposed to drive the transfer from a fossil fuel use to more use of renewable fuels. And during the time of the negotiations, it was argued that the OCCS in fact locked in technologies for fossil fuel use. There was also arguments that the OCCS technologies at this time were not mature enough. I know there is openings to do a revision as the technologies grow maturer, and possibly a change can be expected there. I've also put the CCS directive because the EU ETS points towards the CCS directive for regulations on how the capture and storage should be done to be allowed. In IMO, we have the energy efficiency and carbon intensity regulations, the EEDI, the EEXI, and the CII, which do not have any provisions at the moment for the use of carbon capture on board. And we also have, of course, the IMO net zero framework that was approved but not adopted last year, as you probably all know. There's no explicit mentioning of OCCS in the net zero framework, but I guess you could say that implicitly it's expected to be included in one way or another. And for this, there is a strong need for supporting guidelines that specifies how this should be done. And very important to mention here are the IMO LCA guidelines, the life cycle assessment guidelines, that will show how the actual calculations on CO2 reductions from the use of carbon capture on board will be performed. So, and also in the full value chain perspective, in the well-to-wake perspective. I also put that there may be a need to regulate from other aspects like health and safety and human elements, but this is done in the Maritime Safety Committee and not in the MEPC. So I honestly don't have full information on if anything is ongoing there on the OCCS at the moment. And I also wanted to put the London Convention and the protocol from 1996 that deals with prevention of dumping of wastes and other matters in the sea. And I think they have a chapter, or at least a paragraph, on CO2 dumped under the seabed. I'm not an expert, but I know we have experts in the room if you have questions on that. So like I said, in the IMO there are ongoing discussions on the development of a regulatory framework, and most of those discussions take place in a correspondence group that has been active for 2 years. And that means that many member states and NGOs send representatives to have email correspondence on different issues. And this group is coordinated by Norway. The explicit aim is to develop a regulatory framework for the use of onboard carbon capture and storage, so very much to the point. And includes the objectives of avoiding harmful emissions to air and sea, consider legal barriers to the use of OCCS, transport and transfer of the captured CO2, facilitate access to reception facilities, enable recording and reporting of the relevant data, and develop options that take into account greenhouse gas reductions from OCCS in IMO regulations. So quite a broad spectrum of aspects that need to be discussed. And the discussions are ongoing. There will be reporting to the next MEPC, which is in April-May, but this work is definitely not finished yet. As you can understand, there are many different views on how this should be done. So anyway, this group last year decided that the most important thing would be to develop guidelines. So we're developing draft guidelines for testing, survey, certification and approval of the complete OCCS system on board the ship, with including development of provisions to minimize emissions and its discharges that are harmful to the environment, and to ensure availability of data needed for the LCA calculations. And I mean, DNV's picture of the value chain was a bit nicer, I think, but this is. But I tried to just show that the value chain, that there are many different aspects that need to be included in these guidelines. On this end, of course, it is much to do with documentation, what is needed to be sent into to be sure that the CO2 is permanently storage, but there will also be like onboard service and verifications of emissions, both to air. It's okay. I can look at my notes. No, it's okay. So the correspondence groups works with specifying criteria for all these different things. And since I was asked to mention challenges, I've just written down a few of the matters that are being discussed and where many different views are lifted. It can be anything from type approval, technology neutrality, technology maturity, CO2 purity, and how that should be measured, the data needed for the LCA calculations, the monitoring of the CO2 slip, approval methods and criteria, documentation requirements, inspections and surveys. So definitely a lot of things that should go into these guidelines. And further on the challenges, and this is definitely not a comprehensive list, but I've just listed them and tried to structure them a bit, a few of the challenges that we see, since the regulations should take like a holistic view, of course. We have the carbon capture on board. If we get significant increases in fuel consumption, we have increased amounts of emissions to air and water of other emissions than CO2, of course. There could also be new kinds of emissions that are not regulated this far and that needs to be assessed in one way or another, a risk assessment. And of course, approval of technologies, I've already mentioned that, how that should be done. The transfer to other ships or the reception facility, the amounts transferred need to be in some way documented and certified, and that applies, of course, for the value chain in total. And I mean, this is not specific for the ship industry, but the ship industry, as I consider it, is rather small scale and rather scattered compared to what has traditionally been used in CCS. And I'm not 100% certain, but I think this would require more from a regulatory perspective, because we will need to handle many different document streams certifying that the value chain is intact. Of course, permanent storage or usage needs to be certified, and this is very important. And then the emission accounting practices in the regulations can be very difficult to solve. I foresee this, but the discussions are starting. But you know, the calculations for the net zero framework, then we have the economic incentive, and it needs to be decided if the OCCS can be viewed as a set fuel and technology, which actually means that they are eligible for a reward from a fund. Should that be allowed? Should it be allowed for direct compliance? And so on. And is there a rationale for allowing OCCS in the energy efficiency regulations? This is also a needed discussions, because this is not technology that improves energy efficiency. So that needs to be strongly motivated, I think, in order to allow that. But this is subject for negotiations, of course. So nothing is certain. Thank you.
Thank you, Hulda. Now it's one question. There is time for one question, then it's coffee break. And I think Hulda will stay for the coffee break as well.
I will.
Yes, then you can ask your questions. No? All right, great. Thank you very much.
Thank you.
And we will have some coffee, and we will be back here in 25 minutes, so 11:25. Chairs makes an awful noise when you move them. They should put some padding under them, I think. So, welcome back, everybody. So I got a comment that some people are taking photos of the presentation. That is very good, but you can also mail Caroline afterwards, and she will send you the presentations once we just have checked with the presentators, so we can share their material. So that's no problem. So we will now move into the theme infrastructure from ship to final repository. And we will start with a presentation that actually wins the prize for the longest title today. So here we go. Balancing organ sites, buffering, storage and transport capacity in CCS systems. Insights from a single case study in Sweden. We welcome Juan Pablo Castrello from RISE. Juan holds a PhD in technology management and economics with a specialization in freight transport from Chalmers. Juan works as a researcher at the Maritime Department at RISE with logistics systems for carbon capture and storage, urban freight and intermodal transports. So, very welcome, Juan. Go ahead.
Do you hear me now? Yeah, perfect. Thank you, Andreas, for the presentation and the invitation to this event. It's my pleasure to be here on behalf of our colleagues at RISE and talk about something that moves our hearts, that is logistics. And I joined recently, I joined 5 months ago, and my expertise is in logistics, not in carbon capture, but then we are learning, and I joined this team, experienced team in RISE that have been working on carbon captures maybe since the last 5 years. And what I'm going to present today is one of those initiatives focused on a specific case in Sweden, which for us is very important to put the logistics aspects on the agenda of CCS and not an afterthought. Because there are aspects that definitely will determine the feasibility of the carbon capture and storage systems related to the location, of course, of the storage sites, the distance from the emitters to the final location, the type of fleet that is going to transport that CO2, the different types of vessels, the conditions that the CO2 is transported, the fuel consumption, of course, and the conditions at the emitter side, what infrastructure needs to be there to store temporarily the CO2. Those are aspects that we analyze in this project. I think that is better that I... called Logistics System for Cement Industries, CO2 Capture and Storage. This project started in 2023. We are about to finish, and this is a partnership between RISE and Heidelberg Materials, acknowledging the importance of CO2 capture for the cement industry. As Hannes mentioned before, it's one of the sectors that is heart of a sector. It contributes to the global emissions in around 5% and 4% in the case of Sweden. And definitely carbon capture is something that is in the agenda for this sector. And the purpose of the overall project is to increase the understanding of how cost-effective, reliable, and environmentally sustainable CO2 logistics system for carbon capture and storage can be designed for the cement industry in Sweden. The project is led by Sarah Kilikasland. She couldn't come, unfortunately. But we are a group of colleagues here. Johan is in the room, also Christian, and more colleagues in RISE studying these aspects. The project has several work packages related to the review of the literature available on carbon capture, transport, and storage. all the different actors that are involved in this logistics system, including ports, including logistics operators, including, of course, the emitters, and, of course, regulations that are around that and who is taking part of the decisions. And I will talk about specifically about this working package 3, which is the design of the logistics system, which means how to make decisions about the fleet, how many vessels are needed to transport the carbon that is captured, the size of those vessels, the technology that could work or not for the specific case, and of course the storage on site, and I will explain that in more detail later on. We have a working package 4 related to the development of the design of the ships, the technical requirements for those ships, and Johan is part of that working package. And that's like an iterative interaction because those parameters inform the model that we developed for the logistics design. Then, of course, the implications for the different stakeholders in the system, and, of course, project management and communication. So the working package 3 has as objective examining the potential logistics configuration, so the size of the fleet, the number of tanks needed at the emitter location for transporting captured CO2, exploring the reliability, cost efficiency, and operational implications. And our purpose there is to develop a tool that companies can use to base their decisions related to logistics. We are aware of the several uncertainties that the parameters have for that model, but it's a tool that can dynamically change based on the conditions of the market and the technologies available. The research was funded by the European Union and the Swedish Agency for Economic and Regional Growth. This is the scope of the geographical scope of our research. So Heidelberg Materials is located in this island in Gotland, and they have a terminal where they expect to be used for loading and unloading the carbon capture in Slite. And we took as a reference one storage site in Norway called Northern Lights. So it's one emitter, one sink at the end. And of course, there are several options to transport the carbon from the emitter side to the sink, including, for instance, pipeline solutions that in literature have been studied, and also like we have some figures about the cost and the feasibility in the case of the Nordic countries, which is not that clear so far, but the recommended mode of transport for this kind of operation is shipping. And in shipping we have different solutions or different options. The direct transport from the emitter to the storage site, or the transport using intermediate storage sites, like ports, for instance, that consolidate the carbon from different emitters and then they transport the consolidated carbon to the storage site. We consider this system as a baseline for the company to base future decisions and to be able to compare what happens if they perform the operation by themselves, and then later on compare with other possibilities with logistics providers that can perform the loading and unloading and the transport. So this is the option that we explored, where we have, and this is the flow, so it relates to the map. So here we have the plant. So we have here the tanks, the temporary storage of the CO2, the transport by ship, and then finally the sink in Norway. And these are the boundaries that we explore for the logistics system. And when I joined the project, then I realized that this is like a classic logistics problem of trade-off between storage capacity and transport capacity. If we have many vessels, so we need less temporary storage at the origin, because then they come more frequently, and then we can evacuate the CO2. If we don't have that many vessels, then we need more storage in the site, because then the vessel will go back and forth and will need time while I have to store the CO2 in the site. Otherwise, the company will be forced to emit that CO2 because it's not able to store it. So that's the problem that we are solving. Okay, what is the balance? How many tanks on site and how many vessels so that we equilibrate the system and we get an optimal solution based on different aspects related to the capex, of course, of the vessels, the tanks that they will be used, and the cost of the conditioning, the capex of conditioning. Also the OPEX, the operational expenditures for vessels, buffer, and conditioning, the cost itself of the conditioning process, and the cost itself of the fuel that is, or the assumption of fuel that is used in the ships. The decision variables are mainly two. So how many vessels, what size the vessels should have, and the number of tanks that they should have at the port waiting and temporary storage while the next ship comes and unload the carbon. There are some constraints, and the first constraint is we have to meet the expected amount of carbon that the company is planning to capture. So this annual flow requirement. There should be also an inventory balance. So the tanks have a hill level and a maximum capacity of storage. So they cannot be lower than 5% in their utilization and no more than 90% of utilization. So that's a technical constraint. Also the vessel capacity and trip frequency. So it has to meet the flow that we got from the company, this frequency and the size, depending on of course, on the amount of CO2 that needs to be transported. And finally, the constraints related to pressure-specific technology limits, related to the density, if it's medium pressure or low pressure liquefied carbon. The model has several parameters, more than 40 parameters related to the CO2 captured, as I mentioned before, then the transport and the buffer storage. And actually, the model itself is a classic model in logistics, but the challenge in this case is related to the uncertainties that those parameters have, because we are still in the process of developing or seeing how other actors, for instance, develop new ships, new technologies, the technologies for capture or for transforming or liquefaction of the CO2. Also related to infrastructure, if there will be hubs that will consolidate the CO2, the ports, where they will be located. Also uncertainties about the contracts, for how long the storage will be available for the company, what size, what is the requirement regarding the pressure of the CO2, and the policy and external settings, as we heard before. So there are many uncertainties in the model, which makes challenging the case. And that's why with this project we identify the specific parameters for the company and try to estimate then the optimal design for the logistics system. This is the type of results that we get from the model, which allows us to make a sensitivity analysis based on the annual flow, annual CO2 captured, and how many vessels then the system needs. If it's a vessel of 7.5 K cubic meters in capacity, or 12,000 or 21,000. So it's regarding the capacity of the vessel. How many vessels, if we are capturing 1 million tons per year or 2 million tons per year, how many vessels, and if we need only one type of vessel or a combination of them, alongside with the number of tanks that are needed on site. I hide intentionally the numbers because this is something that we are still in the process of validation with the company and internally with our team. But this is the type of analysis that the company can adjust the different parameters based on the conditions that they have in the market, and then assess the final logistics cost per ton in their system. and also adjust the decision even in terms of the capture. So they avoid local optimum that could be like with a small effort in the level of capture could get more efficiency. So it's overall a tool for decision making related to the number of ships and the number of tanks that they need for the operation. As a conclusion, with the model, I mean, it's evident that the decisions about the investment in the logistics system have to be equilibrated. If we make changes in the annual flow that is captured by the company, it requires updates, coordinated updates in the fleet and coordinated updates in the investment needed for the tanks. The modeling framework provides an analysis basis for the company, also to compare with other solutions, offers from different logistics providers, offers from different technologies that could come in the future, understanding that there are ongoing efforts to update different technologies and solutions in the sector. And regarding the uncertainties, this is one of the biggest learnings, we need to understand case by case what are the conditions. We are not talking here, for instance, about emitters that are inland. Maybe they need to transport the CO2 to the port, but different transport options that need to be included into the model. We didn't include intermediate locations like ports that can be hubs for capturing the CO2 and consolidate the CO2. And those are options that actually we will study in a follow-up project, as Carl mentioned at the beginning, that just kicked off, and where we will explore different solutions, different alternatives, including also different storage locations available in the Nordic countries. So with that, that's overall the presentation about our project. Thank you very much, and I will be happy to answer your questions and also count on RISE as a logistics team for providing this kind of tools and assessing the systems that are out there in this chicken and egg dilemma, who is going first? And we are putting on the table this logistics tool, so on the go decisions can be updated based on what is happening in the market. Thank you very much.
Thank you. Do we have any questions for Juan? Oh. So you mentioned these uncertainties. Is there one that is, I mean, which one is the most hard nut to crack, so to say? Can you single out one of them, or?
Yes, definitely technologies regarding the vessels. So if it's medium pressure or low pressure, the size that is reasonable to estimate the model. We actually, during the week, were discussing the sensitivity of the results and how they change if we are considering like 7.5K cubic meters capacity, or 12 meter cubic capacity, or 21 cubic meter capacity, and who is ordering this kind of vessels, if they will be out there, if they will be available for medium pressure or low pressure of the carbon capture. So is there an uncertainty, okay, how the industry will move? Right. Also the type of technology that the energy source that they will use. Now we, as also Hannes mentioned before, we assume that the fuel is the one that is available right now in the market, but that could eventually change. And we could have scenarios where it's LNG or it's ammonia or it's other type of, and that will change also the results of the model because of the cost of the technology and the energy. So that's a big uncertainty. And also the conditions at the storage site. How they are going, or the negotiation process, because this is not a closed contract, this is an ongoing discussion with the storage site. So how they are going to receive the CO2, in what technical conditions, for how long, what is the capacity of that storage site, so I can count on that for sending the CO2. Otherwise, then the company will have to find other storage sites where they are located, where they are allowed by the regulation, how to establish the contract, for how long, how much it costs. So this is, I mean, just to mention some of the uncertainties that, of course, will affect the model. But so far, it's important to develop these tools, and I will say, in literature, we find these tools in the US, particularly for the development of pipelines, all the estimations of costs. In Norway, also in SINTEF, they have developed these tools for doing the calculations of the logistics system, and now in RISE, we are developing this kind of tools for Swedish companies who wants to assess the logistics implications of the carbon capture.
All right, thank you.
Thank you
so much. So the next presentation will be online, which is always exciting to see if that works or not. It's a presentation by Drazen Turma from the Joint Research Center at the European Commission. And the title of the presentation is Shaping the Future CO2 Transport Network for Europe. Is he online?
Yes.
Okay, you can make.
Yes, I'm online. I don't know if you can hear me.
Yeah, we can hear you. Just give me a second and I will try to get you up on the screen as well.
Okay, perfect. I'll share my presentation first to make sure that everything is working, and then we can start. Can you see my screen now? Okay, perfect. Then we can start, right? Yeah. Okay. First, I'd like to thank you for the invitation. It's a pleasure to attend this seminar, but unfortunately, I could not attend it in person to the other work obligation. But I hope next time it will be different. I'm Drazen Turma, and I'm working for the, like you said, Joint Research Center of the European Commission. And for those who are not familiar with the Joint Research Center, we are Commission's science and knowledge service. We provide independent and evidence-based knowledge and science, and we support EU policies to positively impact society. I'm part of the GRC's Energy Transition Insights for Policy unit, located in the Netherlands. And today I'll be presenting our activities related to CCS, and will dedicate some time on the potential role that Sweden can play in the deployment of CCS technologies and development of the CO2 market. I think the previous presentation was a perfect intro to my presentation. However, we are dealing, let's say, with more high-level analysis that cover the whole EU and wider. So to begin, I won't go too much into the details. Since you are attending this seminar, I believe you are already familiar with the concept and how CCS value chain works and what are the possibilities. So I'll switch to next slide, to the European Commission's policy context and status related to CCS. And the policy landscape has evolved significantly to support deployment of CCS. We've moved from initial CCS directive in 2009 to more recent milestones like the EU Green Deal and Net Zero Industry Act. And for the CCS, the recent important Commission's publications are the Industrial Carbon Management Strategy and 2040 Climate Target Plan, which basically both emphasize the potential role of CCS in Commission's aim to transition to low carbon economy and to become carbon neutral by 2050. Looking ahead, we expect new legislation targeting CO2 markets and infrastructure in the second half of 2026. And when it comes to activity of my unit, we have a long history related to CCUS, and our team is still very active in this area. We are covering the entire CCS value chain. We have many activities, and one of the activities is the Clean Energy Technology Observatory, or how we shorten it to CETO. This is an in-house commission project that monitors research and innovation while assessing the competitiveness of the EU's clean energy sector, and we look at everything from technology readiness level and patenting trends to value chain analysis and global market positioning of EU companies and many more. We are doing it for many technologies, and in the following couple of slides, I will share just a small part of insights from the CETO report on CCUS. Here you can see the QR code. You can download the report and see the latest version. It's being published on an annual level. What we can see is that the global momentum is clear, and based on global CCS Institute data, the number of commercial CCS facilities in different phases of development worldwide grew from more than 600 to more than 700 in year 2025, and with capture capacity that could reach more than 0.5 gigatons per year. And on the right side, you can see that many, for example, capture technologies like absorption are already at technology readiness level 9. There is still, let's say, room for innovation in other capture technologies, but also in other parts of value chain. And EU supports the innovation in these areas. Other parts of the value chain, such as transport via pipelines and ships, they have a really relatively high technology readiness level, and they provide the opportunity to scale up. European companies are, we can say, already strong players in this field. For instance, 7 out of 22 companies with commercially available capture technologies are based in EU, including leaders like Air Liquide, Linde, and Shell. And we see similar European representation in transport and storage, and again, companies like Linde and Total Energies. But what we can see here is that this is maybe related to Sweden, that there are no Swedish companies based on our analysis. And if you have different information, it would be good if you can reach out to us, so we can also include that in our report next version. The European Commission's projections related to CCUS are based on extensive energy and climate modeling, and they show potential for massive increase in CO2 capture, transport, utilization, and storage by 2050. And while much of CO2 will go to underground storage, the projection also shows and expect growth in utilization for example, synthetic fuels and materials, and for example, in construction sector. And but key sector contributing to the deployment of CCS technology is energy-intensive industry, with sectors such as cement and chemical industry, where there are no alternatives to CCS when it comes to the carbonization. This insight is based on the entire EU level, but again, some countries, they have their own specificities. And considering the potential ramp-up of manufacturing of CCS technologies and the recent Net Zero Industry Act I mentioned, there is a need for thorough and detailed CCS value chain identification and mapping, but also planning, what leads me to our other recent activities. So besides the usual top-to-bottom approach commonly used in different energy and climate modeling, we are also applying a bottom-up approach to identify the actual industry needs for CCS and to determine how much CO2 can be captured in different sectors using existing capture technology. Additionally, we are analyzing the extra energy needs and CO2 emissions due to capture at the facility level. So the deployment of CCS technologies are also increasing the in one way the CO2 emissions and energy needs of the facilities. In addition, we are also analyzing the probability of deployment. Since we are dealing with high-level analysis, we also want to see to do the analysis on a EU level, which facilities could be deploying CO2 capture first, and we are taking into account different parameters at the facility level, such as the presence of industrial hubs, then sectoral dependencies on CCS, potential benefits of carbon dioxide removal with BECCS, and also distance to storage site, and also announced transport infrastructure projects. We are also analyzing the cost of capture at the facility level, since costs are, of course, the defining factor. And this chart illustrates that the cost per ton of CO2 capture is really different across sectors, with chemical industries, cement, and waste to energy generally facing a different structure of costs than, for example, iron and steel or refineries. And understanding these cost curves is essential for EU's industrial carbon management. But the full report on the actual needs of the industry for CCS, it will be published in a couple of months. But our goal is to assess the entire CCS value chain, and in addition to capture data, we need to have more information about potential CO2 storage sites that we can use now and, of course, in the future, because we are looking until 2050 and even 2070. As well, we need to know the location of potential storage sites, but also their capture, their storage capacity that is available to us soon and later. And for this purpose, we use among other sources, we use the results of the EU-funded project, GSEU project, which identified potential CO2 reservoirs. You can see on the left side of the slide. And as you can see, the storage in Sweden were not identified, but I will come back to that later. This project is still ongoing, and we expect to have an updated data set, also probably somewhere in summer, with more information on locations that were not assessed within the first version of the data set. But in addition to this, it's crucial to know the current state of affairs. So it's important to have insights into existing and announced CCS projects, and we are also collecting that info in our internal GRC database. Our focus is on commercial facilities. And you can see this on the image on the right side, where the red dots represent capture projects, green dots represent storage projects, and transport infrastructure is represented by lines, and it depicts onshore and offshore pipelines, but also shipping. Now that we know the, let's say, location of and capacities of CO2 capture and CO2 storage sites, as well as the announced projects, our team is trying to figure out how to optimize the CO2 transport network in a best possible way and gain more insights into how the CO2 transport network could be developed by 2050. And of course, what is really important what would be the cost of such deployment of CCS technologies as foreseen by the European Commission. But how do we do that? We have built an, let's say, high-level optimization model where we are trying to optimize the transport routes between sources and sinks and also CO2 hubs or terminals when needed. And our methodology involves clustering nodes due to huge amount of data to make it more computationally manageable. And we are developing potential offshore and onshore pipeline and shipping routes, as you can see on the image on the right side of the slide. And we are also using the estimated costs to ensure the network is both functional and cost effective. So like you said, this image on the right side is basically an input data for this optimization model. And also we expect to have the results of the whole analysis in the form of the report during the summer. But you are probably interested more in Sweden, and when it comes to Sweden, we don't have a lot of data. So I'd also like to use this opportunity to invite you to send us any data on the development and deployment of CCS technologies in Sweden. You think it would be interesting for our work. You can see here that the identified capture nodes based on EC's projections and announced projects, but there are no data on storage potential, like I said before. And with the legal problem of storing CO2 in the Baltics, the option for Sweden is to transport CO2 via shipping to store it offshore in the North Sea or via onshore pipeline. But however, based on the announced projects data, it's reasonable to assume that shipping is more likely to be used, at least in the beginning of the CO2 market development. But in general, our view or opinion is that the development of CO2 pipeline infrastructure, not just in this region, but also in the whole Europe, could be challenging during the early phase of the CCS deployment, and alternative forms of CO2 transport, such as shipping, should be explored. And based on the announced projects, it's realistic to expect that the significant part of CO2 transport will take place through alternative forms of transport to the coast via rails, roads, or even rivers. And this will be followed by shipping to offshore storage locations, which make up the majority of the CO2 storage capacity. That's also important. For shipping, in addition to shorter lead times compared to pipelines construction, it is really important that shipping offers flexibility, and this could be crucial for CO2 transport in the early phase of the network development. And then with further development of CO2 market, where more things will be known, there could be significant progress in CO2 transport via pipelines, since in the long run, it is cheaper. But definitely each case should be analyzed really on a specific cost basis. And for conclusion, we can say that from a technological point of view, CCS is ready to scale up to the levels foreseen by the Commission. And Europe or European Union is currently a global leader thanks to strong policy support, but also on an EU level, but also on a national level. And however, our biggest challenges remain the lack of commercially proven storage capacity, and also the need for a coordinated transport network to make the entire value chain more cost efficient. And hopefully the new legislation I mentioned at the beginning of the presentation, the new legislation on CO2 markets and CO2 infrastructure will bring more clarity and help us overcome current obstacles. But again, I'd like to say that international coordination and collaboration is crucial for the successful and cost-optimized network development. And also deployment of CCS technologies and the successful cost-optimized decarbonization of the EU. And with that, I'd like to finish the presentation and thank you for your, if you have any questions.
Thank you so much for that. Do we have any questions? Yeah, you need a mic because otherwise Drazen can't hear you.
Yeah, I already have. I can hear you, but the sound is not the best. So if you can use the mic,
All right, I will.
Perfect.
Let's see if this works. Yeah, go ahead. Takes a couple of seconds before it wakes up.
Yeah, no problem.
Thank you so much for the presentation. I think it was great to see this large scale and overview of Europe. You showed us a slide indicating cost of carbon capture depending on the capture amount. I think it was between sort of 50 to 100 euros or something. How, in your view, how does that capture cost compare to the total cost, including the logistics and storage or utilization?
Yeah, that's a good question, and the information I think all would like to know, and we'll talk about that more in our report. I mentioned that will be published soon, but it really depends. But based on preliminary results, I would say that if we want to have let's say the infrastructure on a EU level, transport costs are really also significant. And when it comes to capture costs, I think we have more clear situation, more clear picture what we can expect. And when it comes to transport and also storage, the situation is a bit more complicated if you are looking at the EU level, because it also depends on the region and also on some regional specificalities and type of transport, type of storage site. So I wouldn't go into much more details about the costs now until the report is out.
All right, thank you. And
I know it doesn't maybe answers your question, but I would still keep it before it goes public.
Right, thank you. And we have one more question.
Yes, thank you, Drazen, for the presentation. Very interesting. I have a question on you show maps and storage sites and capacity, and I wondered, since they are quite many, do you include enhanced oil recovery in these? Just for a clarification.
No. In general, Commission's view is that EOR shouldn't be, let's say, supported by the Commission because it generates more emission, let's say it like that, in the process.
Thank you.
Yeah. But when it comes to storage capacity and identifying potential storage capacity and locations, we are taking everything into account. Well, the colleagues that were part of the GSEU project, they also took into account of course, the hydrocarbon fields, because with the time they will be depleted, and some of them are already depleted.
All right, great, thanks. Sorry. There is another question.
Okay.
Thank you, Drazen. I'm Sarah from the Swedish Energy Agency. I have two quick questions, I hope. One is like if you, for your infrastructure, if you're considering which quality of CO2 and pressure and so on. And my other question was if the Net Zero Industry Act reporting feeds into your database.
This is a pretty, like I said, high-level analysis. So we are not dealing with, let's say, hydraulic and of the system and the pressures. We are more interested to know, in general, the numbers, the costs that we could expect, the length of the network, so we can, or the Commission can plan the investments in the future and what would be needed to support the deployment of CCS. And sorry, the second question was?
So the second question was, under the Net Zero Industry Act, if the data provided through that reporting, if it feeds into your database of projects.
No. Unfortunately, the scenarios and the reports we are preparing now, most of it's already done, and we didn't get the from our colleagues from Klima and Ener that are dealing with this data. Countries are submitting. We didn't get the information on time because some countries submitted all on time, some countries didn't, and then there were problems with harmonizing data and we didn't get it on time. But we are already working with them on new scenarios that would include this information, but also there are some issues with sensitivity of data, so it would be also on a high level, not too detailed, because then some data, unfortunately, we can't publish it to be available to everybody.
Okay, thank you.
Yeah.
So I think we will put your contact, your email address and so on in your presentation if anybody wants to reach out to you and have further questions or want to complement your report with Swedish numbers, so to say. Okay, great. A big thank you for being here. Thank you.
Thank you.
So now we will just try to find the right presentation again. So, here we are. Good. So, the next theme for today is onboard technical solutions. And first out is Stian Akre from Wärtsilä. Welcome. Stian holds an MSc degree in physical chemistry from Norwegian Institute of Technology. He has been working in the fields of marine and shore-based applications of environmental technology for more than 30 years. Prior joining Wärtsilä in 2010, he served as head of environment for a major Norwegian ship owner and as a consultant within environmental technology and sustainable. The title of Stian's presentation is Onboard Carbon Capture and Storage, Pioneering Solutions for Ships. So, very welcome, and please go ahead.
Thank you, Anders, and thank you for getting the company almost right. It's very nice to be here. You have heard from a lot of very clever experts. I'm going to stay very practical and tell you about the vessel that has already been mentioned, Clipper Eris. What we call the world's first full-scale CCS system. And by full scale, we mean that we capture as much CO2 as possible from all exhaust sources on board the vessel. That means main engine, auxiliary engines, and boilers. But first, allow me a couple of words on my company. Wärtsilä, we are nearing 200 years of age. We are located around the globe, as you probably know. We are also located here in Gothenburg, among other things, with my colleague Lars. I'm located in Norway, where we have our exhaust treatment facility, and that's where we developed the CCS system that is now out sailing. Very quickly, as mentioned, we boldly call it the world's first full-scale system. It captures 50 tons per day from this vessel. That means, and there was also a question about these tanks earlier. They are able to accommodate about 800 tons of CO2, making it possible for the vessel to capture as much CO2 as possible on a transatlantic voyage, for example. Little bit of background. We have heard about legislation today. I'm not going to discuss that in more detail. I just want to show this context, because we are working on all three. We are working on the technology. It's applicable. It has a decent TRL level already, but it's not finalized, and it will probably be developed for many, many years to come. We have chosen our solution as of today. You'll hear a slightly different version a little bit later. The regulation is, of course, key. No one will do this unless they have to, in one way or another. So we are trying to influence those processes. And then, of course, there is a business case, or there has to be a business case in the future for this to work. There was a question about the cost, and it was also mentioned by the previous speaker. We are also in the same vicinity when we calculate, let's say, the cost of captured ton of CO2 on board a vessel with the capex and the opex. We are also around 50 to 70 euros per ton, or dollars if you like. Then comes, of course, that's the CO2 captured and stored on board. Then comes the final fate of the CO2, whether it is sequestration or utilization. And how much you have to pay for that is of course also part of the business case for the ship owner. Okay, this is what we are doing. We are doing post-combustion. I used to call it liquid absorption rather than the amine process, because it's a liquid. It doesn't have to be an amine, but in most cases it will be an amine of some sort, also for us. You need to precondition the exhaust before the CCS system, and in this case we precondition using a scrubber. That allows the vessel to also run on heavy fuel oil if that's something they want to do. And of course we know in the life cycle context using a scrubber is very favorable CO2 wise compared to using low sulfur fuel. So that adds to the, let's say, the total benefit of this technology. Then it's straightforward, and it's been shown earlier today. We have the whole train on board until liquid CO2, which is stored then in the tanks. This is just a snapshot from our test facility in Norway, where we have developed this CO2 system. You can see the absorber in the middle behind the three guys there. That is actually doing the CO2 capture, and then you don't see here the liquefaction plant, but you do see the final stage, which is the liquid CO2 tank. So in this facility, we are also able to run heavy fuel oil. It's not a prerequisite. You can, of course, capture CO2 from any fuel that contains carbon, methanol, LNG, LFO, diesel, or heavy fuel oil. It still works. I will jump to the vessel. This is the vessel in question, Clipper Eris. She was built in 2019. She has a two-stroke heavy fuel oil engine from MAN. She has a quite this is prior to CCS installation. So she already has quite a substantial funnel casing, as you can see, that contains two scrubbers, one for the main engine and a second scrubber for the auxiliary engines and the boiler. It's also provided with EGR, exhaust gas recirculation for NOx compliance, and I'll show you later that that is a very good combination also with carbon capture. But she has a lot of deck equipment, so it's, as mentioned earlier today, space on board is scarce and it's always a challenge. So what we decided to do was to prefabricate a backpack, if you will, to put on the back of the funnel casing, and then we looked for space for two tanks. And you have to, the tank size is of course project specific. It's about your fuel consumption. It's about, first and foremost, your compliance strategy. How much CO2 do you want to capture? Some customers or some ship owners might just want to be carbon compliant, if you will, capturing 10, 20, 30%. Then of course the system is smaller, tanks are smaller, cost is lower, energy consumption is lower. So this is very project specific. In this case, as mentioned, the owner wanted to be able to sail across the Atlantic, capturing CO2, so that was the dimensioning factor for the tank size. Here you can see we have fitted this backpack with a carbon capture system. I'll show you a little bit more detail about that. This box here is the liquefaction plant, and in spite all odds, we were able to fit the two tanks on deck. In this case, there was no compromise on cargo capacity, neither on stability or anything else. So you could say tankers, this is an LPG tanker. They are maybe, or tankers in general, one of the more favorable vessels to retrofit with CCS. Of course, if you do CCS on a new build, there are a lot of benefits that you can have, not at least on the energy side, because this will consume energy, as mentioned. On a new build, you can prioritize CCS first, or at least very high on your list. On a retrofit, you have to try to find whatever waste heat you can find in order to optimize the performance of the carbon capture system. This is during pre-commissioning or pre-construction of the backpack. Here it is. It's finalized then in the yard before the vessel arrives, and then lifted on board along with the tanks that you can see. They accumulate quite some size. They are made in China in this case, and lifted on board the vessel. So it actually is possible. This is a picture of the vessel out sailing. You might say it's too much or it's a lot of impact to the ship, and that is true. But in the name of decarbonization, we have to keep in mind that anything you do in order to really decarbonize, it will have an impact. If you are switching to other fuels, you will have to switch engine, you have to make a lot of additional tank capacity. So it's not a free ride either. And then you could, of course, say, well, I'll go for batteries. Good luck with that. I mentioned EGR. This looks like a shotgun plot. I'm nearing the finish here now, Anders. So just showing that this is performance of the CCS system while we were commissioning. That's why it's all over the place. We were tuning and tweaking everything. But then you can see in the circle, when you do EGR for NOx compliance, then you are basically increasing your CO2 concentration in the exhaust. You are reducing the exhaust amount on the ship. Thereby you are improving the carbon capture performance of the same system. So that's very favorable. Typically people or operators will only use their NOx abatement technology within the NOx ECAs, of course. So you are not necessarily benefiting from that all over the world. Okay, last one. Is it working? I would say yes. This is a third-party laboratory analysis of this captured CO2 on board Clipper Eris. You can see a CO2 purity of 99.98 plus. For comparison, the Northern Lights sequestration site, which is frequently referred to, they have a specification of 99.81. So it actually works. This is what it's all about, I think. It's we have agreed already from the first presentation today that we will be sailing on fossil fuels for many years to come, or at least a large portion of shipping. We have to do something about that portion and solve some challenges. And if you look at these numbers, all these technologies are then installed on board Clipper Eris, and for a conventional vessel, the result is quite nice. Thank you.
Thank you so much. Before I open up for questions, because we are running out of time, you will stay for lunch, I hope.
I will.
Great. Then you can ask question as well during the lunch. But let's have one question if there is somebody that is very eager to ask a question to Stian. There we go. Jakob from Stena.
Yeah, thank you so much. I'm just curious, what is a trigger point for the ship owner and yourselves to but to install and actually commission and run the system?
That's a very good question. Back to maybe my slide with the three almost circles, where the last one is the business case. The business case is non-existent today. That's clear. So you need to have today an additional, let's say, urge or drive to do this, because it doesn't make sense today. We need the regulations and we need the incentives to be up and running. But luckily we have some early movers, and there's to prove this, and we need some vessels out there sailing, capturing CO2, trying to deliver, testing the value chains, and so forth. Otherwise we will never get anywhere. So we have luckily some early movers, and we have a lot of interest. Obviously, because ship owners with large fleets, they are seeking ways to future-proof their fleet or their assets. And this, as we have heard earlier today, will be one of the main opportunities for meeting the future decarbonization demands.
Right, thank you. New technology that lacks business model isn't something new in the maritime business, I think. But as you said, early movers can actually solve that problem, and we see that in different areas. So I'm hopeful, at least. So thank you very much. Now, before lunch, we welcome Laura Lagerlöf from Langtech. Laura is the managing director at Lang Group, a company with solutions ranging from batteries, scrubbers to CCS technology. Moreover, I learned that Laura is the Honorable Consul of Sweden in Åbo. Is that right? Yeah, great. Good. You have vast experience from shipping business, of course, and you will present on Langtech's solutions here today. So thank you for coming, and I think this is really nice. You're from Finland, we have a Norwegian guy, and then we have a Danish guy as well. So yeah, it's quite international. Nordic, yeah. Yeah, exactly.
Thanks. Yeah, now it's on. Good. Many thanks for the invitation, first of all, and many thanks for your patience here. I'm the last speaker before lunch, so when you have been kind and listened to my presentation, then everyone will be rewarded with the lunch. So I'm Laura Lagerlöf, and I already heard a comment that Langtech is not so well known probably here in Sweden, so maybe I start by telling a little bit about the company, and then my presentation will be also quite a detailed, going into the technical details of the carbon capture system that we have installed and now piloting on one of our vessels. So we have Lang Companies is now this is a presentation where these pop in. Okay, yeah, now all there. So we are a family company based in Finland, and we have Langtech is a company where we have since 10 years ago started by developing scrubbers, then we have added ballast water treatment into the products. Now for about 2-3 years we've been working a lot with carbon capture. Also now have added batteries into our products and doing, it's just a process that we are doing type approval for battery systems. So coming also that, but trying to develop various green tech solutions in Langtech. And then a very good combination is that we have also a ship-owning company in the same group of companies. The ship-owning company is Elder, and also our interest for scrubbers has started because we needed the scrubber solution for our own vessels. Today we have 14 vessels in the fleet, mainly sailing here in the northern part of Europe, but also going down to the Mediterranean. So we are very much touched by the new regulations of what ETS also brings, and this is why we have quite a big interest also to develop carbon capture on our vessels. Then in the companies we also have some special containers, especially for steel and heavy bulk products. I don't know, this mic is somehow sitting weirdly in the neck, but okay, maybe it's now a bit better. And my sister is leading then an industrial cleaning company, which is the last one here in the group of companies. But then how we started with the carbon capture. So I mentioned already that Langtech has had scrubbers as the first product. And from the scrubbing systems, we know that if you have a too strong solution of caustic soda in the closed loop scrubbers, then the caustic soda starts reacting with CO2. This in the SOx scrubbers you try to avoid to get this reaction. But then when starting with the carbon capture systems, we actually turned this thinking the upside down, that we want caustic soda to react with CO2. We tested also and were thinking about other chemicals, and as Wärtsilä has amine systems, many others are also working with amines, but we then opted to go with caustic soda as the chemical in the carbon capture. Many of our vessels have quite big engines, so we need some solution for CII also. And we were thinking about all kind of what can you do wind silicone paint to make the ships more energy efficient. But for some type of vessels, the gap is so huge that we didn't find any other solution than carbon capture. So that's then why it's maybe not so common that the ship owner starts testing and developing their own solutions, but we went anyway for the choice to try it on our own. Here are some photos. This is the vessel. Actually, all our vessels are named according to the women in the family. So this is my vessel, Laura, where we have now piloted the carbon capture. And there is a picture taken then. It's quite tight in the funnel, so not so easy to get any photos of the unit, but there is anyway a unit picture here. And then we have additional components in a container on deck and tank containers also on deck. Yeah, so when we were looking for various alternatives to do carbon capture, this idea of using caustic soda, which we already then knew from the closed loop scrubbers, became then the choice, because with the amines the energy consumption is huge, and here we could see that we can manage with the lower energy consumption. And then also caustic soda is already available, or the logistics for caustic soda supply is already available in the ports because it's supplied to closed loop scrubbing. And then also the reaction is quite interesting there. When CO2 reacts with caustic soda, it's forming what we all know as soda ash. And luckily now EU has confirmed that doing carbon capture by turning caustic soda into soda ash, that is counted as chemically permanently bound. So we have the EU proven solution there. Here is then a few areas where then soda ash can be used. In our case, the vessel is going in a liner service between North Finland and the Netherlands. The volumes are of course very small at the moment. We are just testing and piloting. Due to the fact that it's not possible to get any advantage in the MRV reporting, we are not running the system continuously just for testing purposes at the moment. But there is a waste to heat plant in the Netherlands, very close by to the port where this vessel is going every second week, calling there in Terneuzen. So we are now cooperating with this waste to energy plant, and they use soda ash for their own exhaust gas treatment then again. So this has now become a quite good loop for the logistics also of the end product from our vessel. Here is mentioned some other areas where soda ash could be used. Yeah, regeneration could also be one option, but much better to find ways to use it as such, because for regeneration the temperature needs to go up to 650 degrees to get it separated. Okay, now we maybe have all on that slide in place. Maybe a little bit of downside of using caustic soda is that probably the what you need to store on board after the capture process are much bigger volumes than if using amines. Positive side is that you have, as mentioned, much lower energy consumption because we don't do any separation on board. So here you can see how much caustic soda is needed, 2.4 tons for each captured CO2 ton. We use 50%, or delivered on board is 50% caustic soda. We dilute it further with water. So that's why the formation of soda ash is 6.1 tons for each captured CO2 ton. This, okay, and the energy consumption is here mentioned. Maybe it gives a little bit easier picture if I tell it in the amount of 20-foot containers. What we manage it with is 5 20-foot containers, tank containers, that we have on deck for the roughly 4 days sea voyage from North Finland to the Netherlands. And these are in double use, the containers, so when they can be used both as caustic soda storage tanks, and once the caustic soda is used in the process, then these function as storage tanks for the soda ash. And the vessel has roughly 6 megawatt main engine, and we are, by the way, not doing extremely high percentage of carbon capture. We were restricted partly of the component sizes what can be fitted on board, so we take only half of the exhaust gases into the capture unit, and then there the capture rate is 50%. So what we at least now have managed to do with caustic soda as chemical is maximum 50% capture rate, and when we treat only half of the exhaust gases, it gives us an end result that roughly 20-25% of the CO2 is captured. Here is a picture. This vessel is also fitted with a SOx scrubber, so we have the scrubber is underneath here, and then the capture unit, CO2 capture unit, is this tower here. We need for the carbon capture process, we need the exhaust gases to be cooled down. So that's why a scrubber or some other cooling of the exhaust gases is needed before the process. I guess it's the same with the amines also, that for the reaction the exhaust gases need to be cooled down. And there you can see then that the bypass, half of the exhaust gases bypass the capture unit, and here half go into this tower, and there is a fan to force the wanted amount of exhaust gases into the tower. Here then a bit more in detail the process. So extremely simple. The energy consumers are the fan, which is forcing the exhaust gases into the capture unit, and then a circulation pump to circulate, like in a closed loop scrubbing system, also circulating the process water in the closed loop. We have 2 tanks and keep circulating the same batch of water until the batch is saturated, not reacting with CO2 anymore, and then simply swap it to the other batch, which is then the tank is filled with fresh caustic soda and water during the time when it's operated from the other tank, and the saturated tank is then always emptied to the tank containers on deck. And there is CO2, like in a SOx scrubber system also is a SEMS measuring the CO2 content before and after the capture unit. And caustic soda and water supplied into the process tanks. Yeah, as mentioned, with vessels using heavy fuel oil having a scrubber, it's the advantage that the exhaust gases are already cooled down. With low sulfur fuels, some cooling of the exhaust gases would be needed, so that we get the exhaust gases roughly to 70 degrees is the ideal for the carbon capture reaction to happen with caustic soda. Here was we were talking about also the cost. So here I can mention that we have quite good balance is that buying the caustic soda and selling the soda ash is OPEX-wise roughly the same cost. So at least in today's market, the OPEX is almost zero. Of course, you have logistics cost and such, but the ton price of both is roughly the same. Yeah, and we spoke about carbon capture in the sense that does it prolong the use of fossil fuels? But we have the opinion that no, absolutely it doesn't, because nothing restricts using carbon capture also if you are burning biofuels. If we are aiming for zero emission vessels, so we should actually combine carbon capture with use of biofuels or green methanol, whatever is the greener fuel compared with fossil fuels. Yeah, now I exceeded 1 minute already, the lunch break time, so I'll end here. If you have some questions, maybe we have time for one or two, but depends on how hungry you are.
I think there will be a question or two, but first of all, thank you so much.
Thank you.
Do we have any question? No, crystal clear. So we're talking a lot about technology, rules and regulations and so on, but what is the comment from the crews on board? Maybe you have some experience from the crew on board. There's a new system that they need to learn, and is there any safety issues and so on that?
From that point of view, the crew on this vessel is used to deal with caustic soda because they have the closed loop scrubber already on board. But I have to say that our crew has had to be involved in the product development a lot. So they have had a lot of extra work with this project. So, but of course, for next versions, we would tend to make them more auto. This first one is very manual and a lot of development work still on it.
Stian, do you have any comments on that from the company with a strange name? Yeah.
About the crew, you mean?
Yeah.
Yeah. In our case, or the Solvang case, there's one extra crew member on board because, of course, the size is quite significant on that system. Luckily on that vessel, it's an LPG carrier. They have a liquefaction plant already. They are very well known to handle gases in different stages. So we're luckily with the competence of the crew. But of course, there's more work, like Laura is saying. Most of the work, however, is then straight up maintenance. It's maintaining pumps, maintaining valves. So it's basically well known to the crew, but there's more work for sure.
Yeah, right. Thank you. So now I won't hold you anymore from lunch. Thank you again, and
Thanks.
We will have lunch until 13:35, right, Caroline? Kvart i till och med. All right, to 30. That's strange. That's wrong in my. Okay, so it's 13:45. Yeah, great. So 1 hour. It's the Easter way.